Welcome back, ladies and gentlemen. Today we're going to tackle section 11.2, and up on the screen you'll see your exit question for the day. I'm going to start you off with all three theorems that you have for the day: area of a trapezoid, rhombus, and kite. The cool thing about having these three theorems is that two of them have identical formulas. The area formula for a rhombus and the area formula for a kite are both 1/2 times the length of the diagonals multiplied together. The other thing that you can do for these, instead of using this particular formula, is to simply break it up into triangles. And remember, one of your properties for rhombus, rhombi, and kites is that the diagonals are perpendicular to each other, so those are nice right triangles that are easy to find the area of in most cases. This one's a little bit of a throwback. You should remember that, but the area formula for a trapezoid is 1/2 times the height of it as drawn on an altitude times the sum of the two bases together. And just like before, we have to work from the very basics, in this case the postulate that the area of a square is 1 square unit, so we need to relate the area of each of these back to a square. Now we've already done some work on that. We've turned a triangle into a parallelogram, and then turned that parallelogram into a rectangle, and then we've turned the rectangle into a square. So we can use that knowledge that we know the area of a triangle and a parallelogram to help us figure out the area of a trapezoid and a rhombus and a kite. So first, this one seems pretty complicated. That area formula seems pretty complicated, and you might wonder why that comes about. Well, if we take a trapezoid and double it and flip and rotate it and lay it next to itself, through some pretty easy proof, you can show that we've now just formed a parallelogram on the outside of it. And the area formula for the parallelogram is how tall the parallelogram is times the base of the parallelogram. So this distance right here, which would be, in this case, B1 plus B2. But notice that for this trapezoid that we wanted to find the area of, we have two of them, and we really just wanted to find the area of them. So we find the area of the parallelogram and then chop it in half, which is height times the sum of these bases and then divided by 2, which is basically exactly what that formula says. Kites and rhombi, on the other hand, are easily divided up into right triangles. And right triangles, for instance, if we were to find the height of this triangle right here, not even a right triangle, but just the triangle right here that I'm outlining, the height of that triangle is 1/2 of the first diagonal. And so if we were to find the area of this triangle, it would have a base of d2, so we'd go 1/2 d2 times the height of it, which is 1/2 d1. And you notice now I have two factors of 1/2 in there. But since I've only found the area of the top half of the kite in this case, I have to multiply my entire expression by 2 to get the full area of the kite. So if I took those two factors of 1/2 and multiplied it by 2, I would just end up with 1 factor of 1/2, which is what we see in the formula. And you can make an exact same argument for this rhombus over here. Our first example today is worth doing because I'm going to emphasize the importance of exact values here. So our job is to find the exact value of x. It's worth your time to copy down the drawing and label it as it sits. All right. To get started, take a look at your drawing, and you notice that you have some information about the bases and the height and the area. So we have a lot of the variables that are included in the trapezoid, area of a trapezoid formula. So we plug in as many as we can, 14, and then we have 3 times the square root of 2 and 4 times the square root of 2, and the only thing we don't know is this height right here. So we start working with it, and you'll notice that we have like radical terms here. These are kind of like terms, so we can simply add them together. I have 3 square roots of 2. And over here I have 4 square roots of 2, so in total I have 7 square roots of 2. Then to start unwrapping that, I have to get rid of this factor of 1/2, so I'm going to multiply both sides of the equation by 2. And then I need to get rid of this factor of 7 times the square root of 2. And you'll notice that it's multiplied by x, so I can divide both sides of the equation by that, which gives me a pretty good mess over on the left-hand side. You'll notice that 28 is divisible by 7. You get 4. But now we have a radical on the denominator of a fraction, which remember is not allowed, so we need to rationalize that fraction. So we're going to multiply by a fancy version of 1, square root of 2 over square root of 2. and simplify what we get. So we get 4 times the square root of 2 over 2, and of course the 4 and the 2 can simplify to get our grand total of 2 times the square root of 2, and then of course we have to put a label on there, and since what we found was a linear length, we're just going to keep it as centimeters, plain old centimeters, not centimeters squared. Our next example has very few labels on it, but we can totally find the exact area of the rhombus. Why don't you copy down the drawing? Okay, this relies on you remembering just a couple properties about a rhombus, mainly that the diagonals are perpendicular, which splits this rhombus up into 4 not only right triangles, but 4 congruent right triangles. And we are going to use the area formula. There's a lot of ways to find the area of this rhombus, but we're going to use the area formula. So I'm going to write that down, which means I need to know the length of each diagonal. And since this is a right triangle, this is a very special 30, 60, 90 right triangle. So in order to find the other lengths of half the diagonals anyways, I would chop this in half to find the short leg, and then I would take that short leg times the square root of 3 to get the long leg. And then when I plug this into the formula, this long leg is only half the diagonal, so I'll double it, and this is only half the diagonal, so I'll double it again. So I have 4 times the square root of 3 for that long diagonal right there, and I have 4 for the short diagonal. And then it's just a matter of multiplying the right things together. Remember, you can combine everything on the outside of the radical together to get 8 and leave everything inside the radical alone. Just remember to put an appropriate label on your answer, meters squared in this case. There's your assignment for the day. I'll see you next time.